This lecture's on rational functions. In class we covered the introduction and the domain restrictions and effects. This lecture will cover the second part, which is end behavior, which includes both horizontal asymptotes and slant asymptotes. Okay, so the end behavior for rational functions. By end behavior, I mean what happens when x grows unbounded in either a positive or a negative direction. Well, to find the end behavior, you want to use the general or expanded form of a polynomial. So use the general or expanded form. And you want to compare the leading term of both the numerator and the denominator. Okay, so suppose that you have a rational function f of x, and we have in the numerator one polynomial nx, and then in the denominator we have another polynomial dx. Well, in expanded form, we could write nx as a n to the xn plus a n minus 1 to the x minus 1 plus all the way down to a1x plus a0. a0 is going to be your constant term, and an to the xn is going to be your leading term for the numerator polynomial. And in the denominator, let's say we have bm xm plus bm minus 1 xm minus 1 plus all the way down to b1x plus b0. So here b0 is the constant term, and bm xm is going to be the leading term. So for this rational function, we're going to have n is going to be the degree of the polynomial xn. M is going to be the degree of the polynomial d, and the leading coefficient of xn is going to be an. So that's the leading coefficient of xn, and then bm is going to be the leading coefficient of dx. So we're going to consider three cases. In the first case, case 1, we'll consider the case where the degrees of the numerator and the denominator polynomials are the same, i.e. n is equal to m. So this is going to be case 1. When this occurs, we're going to have a horizontal asymptote. And the equation for that horizontal asymptote is going to be y equals an divided by bm. And the behavior here is going to be written in arrow notation as x goes to either positive or negative infinity, f of x approaches an divided by bm. Let's look at an example. Suppose you have the polynomial 10x squared divided by 3x squared, say plus 1. Well, in this case, again, we want to look at the leading term in the numerator and also the leading term in the denominator and compare them. And you see that the degree of the first polynomial is n, and that's equal to 2, and m is also equal to 2. That's the degree in the denominator polynomial. So we have n equals m. That means that there's going to be a horizontal asymptote, y equals an divided by bm, and in this case the leading coefficient on top is 10 and the leading coefficient on the bottom is 3. So what does that look like in terms of the graph? Okay, it's x and y. So we want to draw a horizontal asymptote at the value y equals 10/3, and we can draw that one as a dashed line in red and then label it y equals 10/3. And the graph itself, let's see, we know that it goes through 0, 0, and it's going to be sort of a bowl-shaped, and then it's going to approach y equals 10⁻³ on to the right, and also it's going to approach y equals 10⁻³ to the left. So that's that graph for the first example. Okay, let's look at another example, or another case, I should say. And in this case, we're going to have, so this is case 2, we're going to have n less than m. So the degree in the numerator is less than the degree in the denominator. We have a horizontal asymptote. For this case, and the equation for the horizontal asymptote is going to be y equals 0. The arrow notation would be as x goes to either positive or negative infinity, f of x is going to be going to 0. Let's look at an example. Suppose you have 5x divided by 4x² plus 4. So let's see, leading term in the numerator, do that in red, is 5x, leading term in the denominator is 4x². So in this case, let's see, n is equal to 1, the degree of the numerator, and m is equal to 2, the degree of the denominator, and we have 1 is less than 2. So we're going to have a horizontal asymptote, and the equation is y equals 0. Let's look at what this function, the behavior of this function at the ends. So again, we want to draw this horizontal asymptote, and it would correspond to the x-axis, and that's y equals 0. Let's see, we have y here and x here. And let's see, the graph. Let's see, when x is 0, we have 0. And then the graph is going to curve up and come down and approach that asymptote to the right. And it curves up and comes down and approaches the asymptote going to the left. All right, let's look at the next case, case 3. And in this case, we're going to consider the degree of the numerator is equal to the degree of the denominator plus 1. And in this case, we have what's called a slant or an oblique asymptote. So a slant or oblique asymptote. And the equation of the asymptote, let's abbreviated as SA, is going to be y equals mx plus b, where this is an equation of some line which we would need to find. So this right here is going to be an equation of a line with slope m and y-intercept b. So this is a linear asymptote that is neither horizontal nor vertical. Let's look at an example. Oh, and let's do the arrow notation first. As x goes to positive or negative infinity, f of x is going to be approaching this equation of this line mx plus b. Okay, now let's look at an example. Suppose we have f of x equals 27 minus x cubed divided by 4x squared. So in this case, again, the leading term in the top is going to be minus x cubed, and the leading term in the bottom is 4x squared. So n is equal to 3 and m is equal to 2. So we have 3 is equal to 2 plus 1, so we're going to have a slant asymptote. To derive the slant asymptote, we're going to use polynomial division, which I'm not going to cover right now, but I will give an example of that. So let's see what this graph looks like for this function. Okay. The slant asymptote, it's going to be a line, again, neither vertical nor horizontal, and it goes through 0, 0, and looks something like this. Okay. So this is our slant asymptote. Okay, what's the graph look like? Well, let's see. This graph is going to has a vertical asymptote here, and then it crosses over the x-axis, and it's going to approach, as x goes to positive infinity, it approaches our slant asymptote from the top, and then similar way, it approaches the slant asymptote from the top as x goes to negative infinity. So this would be an example of a slant asymptote for this function. So case 4, you could consider n greater than m plus 1, and there are different types of asymptotes you can have. They're outside the scope of this class. All right, now let's look at some examples. We sort of put everything together. So we're finding vertical asymptotes, horizontal asymptotes, or slant asymptotes, x-intercepts, y-intercepts. Let's see. So for this example, find a rational function with these properties. Okay, so we want a vertical asymptote x equals -4, and also x equals 12. So there are two vertical asymptotes. We're going to have a horizontal asymptote at y equals 5, and then suppose that we have x-axis intercepts at say x equals plus or minus 1. So these three properties. Well, let's see. What are the implications for our function? So for the vertical asymptote, this is going to indicate the denominator factors. So the denominator factors, and we're going to have two factors in the denominator. We're going to have x plus 4, that gives us our first asymptote, and then we're also going to have x minus 12, and that gives us our second vertical asymptote. If you have a horizontal asymptote of y equals 5, that means that the leading terms are going to look like this. 5, or the ratio of the leading terms will look like 5x to the n divided by x to the n. And then the x-axis intercepts at x equals plus or minus 1, means that the numerator is going to have two factors, and those two factors are going to be x minus 1 and x plus 1. So what does our function look like? Our function, let's call it our x. Let's see, again, we need, the numerator has x minus 1 and x plus 1. And we also need a leading coefficient of 5. And then in the denominator, we're going to have x plus 4 and x minus 12. So that's one example of a rational function with those characteristics. Okay, let's look at another example. Okay, suppose that you have these properties. So find another or a different rational function with these properties. Okay, so suppose that this one has no vertical asymptotes, and let's say that it has a horizontal asymptote at y equals 3/2, and then let's say that there is an x intercept for x equals 4, and let's say that the function bounces at that intercept. So the curve bounces. All right, what do those three properties imply for a rational function? Well, with no vertical asymptote, that means that the denominator is never 0. And also note that there is no holes. Okay, so you also need the property of no holes and no vertical asymptotes to say that the denominator is never 0. If the horizontal asymptote is y equals 3/2, then that means that our leading terms are going to be of the form 3x to the n divided by 2x to the n, and then an x-intercept of x equals 4 means that the numerator factors, and it's going to have the factor of x minus 4, and since it bounces, that means that it's going to have even multiplicity. So we could square it, for example. All right, let's do, let's make our rational function. Rx equals, so again, we need to have the factor of x minus 4 to some even multiplicity, let's just say 2. And then we need to have 3 and a 2 on the bottom. So we could do 2x squared, but remember that the denominator is never 0. So for example, we could add 1 to that. So this rational function satisfies all of those properties. And if we drew the picture, let's see. X, Y. Let's see. We know that it's going to bounce at 4. Okay. And we know that it has a horizontal asymptote of y equals a half. So let's draw that one in. Y equals 3 halves, not half, 3 halves, sorry. Okay. So the function looks something like this. It's going to approach the horizontal asymptote as x goes to infinity, and say it comes down, hits 4, crosses over the asymptote, and it's going to go up, and then have an end behavior again, approaching the horizontal asymptote on the left. So one thing to note about this curve is that a rational function may or can cross its horizontal asymptotes. So that's one thing to notice about this particular graph. Okay, let's see, let's do one more example. Let's do one with a slant asymptote. So third example, sketch a rational function with these properties. Vertical asymptote of x is equal to plus or minus 1. So there are 2 vertical asymptotes. Let's just say there's no holes. There's no horizontal asymptotes, but there is a slant asymptote of y equals x plus 2. Let's add concavity to this. Let's say that it is concave up on these 2 intervals, negative infinity to 1, and 1 to infinity. Oh, actually, now I look at my problem, it's not plus or minus 1. There's only one vertical asymptote, and it is at x equals 1. There we go. Okay. So we're going to sketch it. We're not coming up with a function, but we're sketching a rational function here. Let's see, let's add some points too. Let's add these points. Suppose that we have the point -3, 0, and 0, 3. So that's an x-intercept, that's a y-intercept. And then let's also add the point 2, 5. All right, what does that graph look like? So if you're not really sure where to start, it's always useful to start by graphing your asymptotes. So we have an asymptote at x equals 1. Let's vertical asymptote. We also have a slant asymptote at y equals x plus 2. So let's see, when x is 0, we're going to cross at 2. Let's put 2 here, 1 here. And it has a slope of 1. So let's see, it looks like, across here, 1, 2. So when x is negative 2, y is 0, so it's going to look something like this. Okay, and this is y equals x plus 2. And then we said it's concave up from negative infinity to 1. Okay, so by concave up, that's going to mean, you know, it's going to look like a cup that holds water. And let's also plot the points here. That will be helpful. So we have the x-axis intercept is negative 3, 0. So let's put some points on here. Negative 1, negative 2, negative 3. So it hits at negative 3, 0. We also know, let's see, 1, 2, 3. We also know it has a y-intercept at 0, 3. Okay, and then let's see, this is 1. Let's put 2 here. So 3, 4. Okay, so up here would be the point 2, 5. So that's the point 2, 5. This is the point 0, 3, and here's the point negative 3, 0. Okay, so remember that the graph cannot cross its vertical asymptote. And because it's concave up, we could think of the graph as doing something like this, okay? Where it's getting closer and closer to its vertical asymptote, x equals 1 from the right, and it's getting closer to its slant asymptote, y equals x plus 2, as x goes to infinity. And then on the other side, let's draw it like, say, this, okay? It's going down through here, and then it's getting closer and closer to the vertical asymptote, x equals 1 from the left, and then it's getting closer and closer to its horizontal or slant asymptote as x goes to negative infinity. So the graph might look something like this. Okay, well, that's it for the second part of this lecture.